Okay, so I'm here today to share sort of the status and some of the latest results from the InSight mission to Mars. InSight, as many of you know, is a NASA mission in collaboration with several European countries to put a geophysical station on Mars to investigate its deep interior. Um, and let's see if I can get this to. Okay, so here's sort of the outline of the status of the InSight mission up front. So we've completed our prime mission last November, almost a year ago, and we're about a year into our extended mission right now. And the lander and its instruments are all still in excellent condition. We're operating around the clock on Mars, collecting science data. We do have impact to our power system from dust accumulating on the solar panels. This was expected, and we're now, I say, we're not able to run all of our instruments all the time, but we are running the seismometer around the clock. It's our highest priority instrument, and we're operating some of our meteorological sensors, pressure and wind, and the magnetometer as we have power. We just passed through an energy minimum this past summer. In August, it was a combination of aphelion, when Mars is the farthest from the sun in its orbit, plus winter solstice, which is kind of our minimum seasonal energy. And we're now increasing our energy. But as this has happened, of course, we're now also going through solar conjunction, where Mars passes behind the sun with respect to the Earth. And so we've had sort of a blackout in our communications for about 2 weeks now, and we should be coming out of that tomorrow. Actually, we should get our first downlink after solar conjunction, and we'll see what the state of our spacecraft is for the last 2 weeks. Meanwhile, InSight's been taking data during all this time during the communications blackout, and that data has been stored either on the lander or on one of the relay orbiters that we use to bring most of our data back to Earth, either the Mars Reconnaissance Orbiter or the ESA's Trace Gas Orbiter. So we should get a pretty big data dump for about 2 weeks of data pretty soon. And I think that the big news, at least from my point of view, is that InSight's completed all of its primary science objectives and has produced, for the first time, a map of the deep interior of Mars, the crust, mantle, and core, something that we only could speculate about before, and now we have hard measurements to tell us what the inside of Mars looks like. Okay, so a little bit about the dust situation. So these are our two pictures of the East Solar Array. We have two solar arrays. These are about 2 meters across for scale. The picture on the right was taken on the 10th day of after our landing on Mars, and the one on the right was taken on the 578th day. We are now at Sol. Today, I think it's Sol 1020 roughly, and so even the panel on the picture on the right is an underestimate of the amount of dust on the panels. And we're at about 20% efficiency on the solar panels. So this is quite a bit lower than what we started the mission on. We started with more than what we needed. We made sure that we had enough solar panel generating power to get through our prime mission with some margin. So far, as I said, it's taken us through another year. We anticipate going at least another 6 months into the next year and possibly longer, but we'll have to see what happens. We're looking at ways of operating at lower energies with more efficiency, and also ways of trying to increase the energy from the solar panels. One thing that we have been able to do is we've actually been able to increase our energy output from the solar panels by a novel cleaning approach. And this video shows sort of a time lapse of what we did. It's a series of stills taken by our camera, which is mounted on the arm, and it goes through the process of scooping up some soil and sprinkling it on the solar array. So here we're scooping up the soil, and then we'll move across the spacecraft till we're near the solar array, and then we dump the soil basically on the spacecraft deck. And what the theory is that we would then allow the wind to carry that sand onto the solar panel. And as the sand bounced across the panel, rolled across the panel, it would knock the dust loose and provide a little bit of cleaning. And let's just see if we can just get here. You can see, okay, here the solar panel is clean. Here it's a little bit darker. Can you see the difference between these two frames? That darkening is the actual removal of some of the dust that was on the panel. And so we were able to actually clean some of the dust off. We got about a 10% cleaning of the solar panel, which actually allowed us to run our instruments during the lowest power part of the season, which we probably would have had to turn them off if it hadn't been for that. And we're looking at other ways to clean the panels off and extend our lifetime, so we'll see what happens in the future. Okay, so these are the so-called level 1 science objectives for the InSight mission. Our overall objective is actually to understand the formation processes of terrestrial planets. And to do that, we're going to Mars as a sort of a laboratory and looking at the structure of its interior, the thickness of the crust, the structure of its mantle, the size and density of the core. And these are all things that are diagnostic of the processes that happened 4.5 billion years ago to form the planet out of the solar nebula. So I'm not going to go into the interpretations of that because that's still work to be done. But in order to be able to understand the structure of the planet, we had to make these measurements. And so we use seismology and precision tracking of the planet to do this. Just to go back and look at the same kind of process on the Earth, back in the late 19th century, early 20th century, we went through the process of trying to figure out what the interior of the Earth looked like using seismology. And it took us about 50 years from the very first detection of an earthquake remotely back in 1889 to the finally having the thickness of the crust, the size of the core, the detection of the inner core, and finally the distribution of earthquakes around the Earth. It took about 50 years to do that. For InSight, we have enough hubris to figure we could do that in 2 years. And actually, we were able to do that. And we're able to take the structure of Mars and put it in context with the Earth and the Moon. This is a figure from the Encyclopedia of the Solar System that was written in 2014 before InSight was launched. And you can see the structures of the Earth, Mars, and Moon are similar in outline. They all have a crust, mantle, and core. But I think the salient thing about this picture is noting that there's question marks next to all the things on Mars. We actually have measurements of the lunar crust, the lunar core from the Apollo seismic experiment, largely back in the 1970s. But Mars has remained pretty much an enigma in terms of its internal structure. We had guesses based on analogy with the Earth, and we have some rough data from moment of inertia and things like that, but we really didn't know what the interior of Mars looked like. So we sent InSight to sort of delineate these things. It has 3 main experiments: the seismometer down there on the lower left, showing its wind and thermal shield over it. We had a heat flow probe, which unfortunately was unable to penetrate down to its 3 meter depth in order to get the heat flow, and that was a disappointment. But we also have the radio science experiment, where we use the tracking of the spacecraft to actually look at the rotation of Mars, and specifically to look at the movement of the North Pole of Mars, the rotational axis of Mars. And then we have a whole bunch of other sensors that were there mostly to support the seismometer and to take measurements of things like the wind, pressure variations, magnetic variations, to be able to separate the noise from external effects from the seismometer itself. And that's very important because we're making extremely sensitive measurements. We expect fewer and smaller quakes on Mars than on the Earth. And so we had a sensitivity target. You can see that the number here, 2.5 times 10 to the minus 9 meters per second squared per root hertz. Just to put that in perspective, that's equivalent to displacement amplitudes at the surface, vibrations at the surface with amplitudes smaller than a hydrogen atom. Okay, and in order to do this, you have to minimize or compensate for all the noise sources. And there's lots of sources of noise. There's noise from the instrument itself, there's temperature variations, wind, pressure variations, and so forth. And the bottom line is we ended up being very successful on this. This chart shows the noise measured on Mars. That's that kind of bluish green cloud through there. And you can see over on the left, these are the levels. It gets down to about 10 to the minus 10 meters per second squared, compared to the Earth, which are the gray lines, about 1,000 times higher. So we're getting noise levels that are 1,000 times lower than can be achieved on the Earth, because Earth is such a noisy place with its oceans and atmosphere. And again, just for context, the accuracy of our sensor, our so-called VBB sensor in the seismometer, is about the size of a hydrogen atom, twice the Bohr radius of a hydrogen atom, which is kind of an amazing feat if you think about doing this in the dirt on the environment of Mars, 40 million kilometers away. So here's what our data looks like. This is the actual seismic data that we look at. A little bit different than what you might be used to seeing. This is called a spectrogram, and it runs from left to right in time. It starts at midnight on the left and goes through noon in the middle and midnight on the right. And then we have the spectrum from low frequencies at the bottom, high frequencies at the top, and then the intensity of vibration at those various frequencies is shown in color. And on this, we have several things. These lines that go across are so-called resonances. Most of them are from the lander. The one at B is actually from Mars, and we don't quite understand that yet, but it's quite interesting. And then we have these spikes at the bottom, which are glitches, and these are just sort of the thermal pops that occur as the seismometer goes through a 100-degree plus or minus temperature changes over the day. And finally, up here at C, we have Marsquakes, and these little smudges are the Marsquakes, and then you can expand them in the time domain to see something that's a little bit more like a seismogram that you might be used to looking at. And we can do that for the entire mission. So this is all the seismic data in one plot. Each line going across is one of those seismograms sort of collapsed down to a line, and you can sort of see the pattern of activity during the course of the day. And of course, so we have the beginning of SEIS operations on Sol 80 at the top to today at the bottom. And we also have time running from left to right across the this chart. And you can see that we have quiet times in the evening and very noisy times during the day due to turbulence and so forth. And it varies a little bit during the year. And overlaid on this are our Marsquakes. And we actually have sensed almost 1,000 Marsquakes over the 1,000+ sols of the mission so far. And you can see most of them are detected during the quiet times. We see very little during the noisy times because Marsquakes are quite small. For the most part, we see a few of them during the daytime, but this is the data set that we're working from. Here's what a seismogram looks like. This is one of our nicer ones. You can see the P wave and the S wave that starts to allow us to get things like distance and start to look at the velocity structure of the planet. You can also see one of those glitches that happen here. This is something we have to filter out when we do our analysis. And we're able to actually locate some of these events. Even though we only have a single seismometer, we can use some advanced seismic techniques to actually get not only the distance, but also the direction and location. We've been able to locate 5 quakes so far, and they're all located in the same region. And that region turns out to be one of the tectonically youngest parts of Mars. We have faults here and volcanism that have been dated to be less than 10 million years old, maybe even less than 2 million years old. And what InSight is telling us that these things are still active today, which is pretty fascinating. We recently published some results in Science magazine, 3 different papers showing the thickness of the crust, the structure of the mantle, and the properties of the core, which were our basic science requirements. The first one was the thickness of the crust. And we actually used a pretty interesting technique. We can't just use the techniques we use on the Earth because we only have one station, but we use some advanced techniques. Again, it's sort of using seismic waves the same way that you would use light waves in optics, looking at how it refracts as it goes through different layers with different velocities, and reflects off these layers. And by looking at multiple paths and multiple bounces, we can actually pull out the depth of various different layers beneath the surface. And we've been able to do this to figure out the thickness of the crust. There's actually a little bit of ambiguity that we have either a 2-layer crust that's about 20 kilometers thick, or a 3-layer model that has about twice that thickness and basically has another layer added to the bottom. And these crustal models have different implications for the amount of heat-producing elements that have been concentrated in the crust, things like uranium and thorium, and for the density. And so we're using this to better understand, again, the formation of the crust 4.5 billion years ago. We're also looking at the structure of the upper mantle. We can use the seismic waves sort of like a CAT scan by looking at various different paths through Mars and looking at the way that those paths affect the seismic waves. And in order to compensate for, again, not having multiple stations, we actually use multiple paths from the source, the Marsquake, to the station by looking at bounces off the surface where it comes down, goes back up, bounces off the surface, and allows us to get multiple paths that then allow us to figure out the distance and the properties of the path. And we can sense down to about 900 kilometers, and we can see that Mars has a low velocity zone, which is there because of the temperature gradient, the heating of the Mars's interior, and starting to give some clues as to the composition of the inside of Mars. And finally, we've been able to measure the distance to the top of the core by looking at bounces off the core, the bounces of S-waves off the core that come back up to InSight, and been able to pin down the radius to about 1,830 kilometers. And this is actually quite large. It's barely within the range we were expecting, but we sort of expected things to come in around 1,700 kilometers. And that has some really interesting implications for the formation of Mars. I'll talk a little bit more about that in a few slides. To do that, we're looking at also, as I said, the wobble of the Martian rotation axis. It wobbles on 2 different time scales. One is the precession, which takes about 165,000 years, and that's tied to the moment of inertia, which tells us something about how mass is concentrated into the heavy core. And that's been measured before by Mars Pathfinder and also by the Spirit rover. We've been able to get a better measurement of that, but the real contribution of InSight is getting the nutation, which is the wobble on top of a wobble that happens on multiple times per year. And we've been able to measure that so-called nutation, and by combining that with our knowledge of the behavior of materials at high pressures and temperatures, we can constrain the radius of Mars just by looking at the size of this polar wobble, which turns out to be about 250 meters that it wobbles back and forth over the course of a year. This allows us to also constrain the radius. It doesn't constrain it as closely as the seismometer, but it is an independent measurement that gives us more confidence in our seismic measurement. But we're also able to estimate the density from this, and the density corresponds to about 6,000 kilograms per meter cubed. This is very small, as you would expect from a large core. You have to have a smaller density to make the total mass come out the same for the planet. Pure iron would be about 6,500 kilograms per meter, and so you have to add lighter elements into the core sort of dissolve these lighter elements. And the most likely one is sulfur, but you'd have to have about 25% sulfur to do that. And so far, our geochemical models won't really allow this. And so we're kind of going back to the drawing board and trying to refine our models and understand how we can get such relatively low densities of the material in the core. So going back to our illustration from the encyclopedia, what I wanted to do with this mission was to rewrite the textbooks. And so this is the first textbook that we'll have to rewrite. Going back to Mars, all those question marks are now gone. We've been able to establish that the core is liquid. I didn't show a slide for that, but that's the character of those mutations show that the core has to be liquid. We're able to get the thickness of the crust. We're able to get the size of the core. We're able to actually look at and detect some of the transitions in the mantle, where the mantle minerals actually switch their crystal structure to a higher pressure structure, and the corresponding boundaries in the Earth can be seen on Mars. The lower one isn't actually even, doesn't even actually exist on Mars, because the core is large enough that it actually occupies that position. So we have iron there instead of silicates. So that's the 670 kilometer transition zone on the Earth doesn't even occur on Mars. So we don't have any material on Mars that corresponds to the lower mantle material on the Earth, which is fascinating for geophysicists, and again has implications for how Mars loses its heat through convection and so forth. And so for those of you who start thinking about other things and dozing off when you see plots of seismology and stuff, we do have imagery. We have 2 cameras on InSight. All these images are actually available on our public website at mars.nasa.gov/insight. New images are actually posted automatically before the scientists even get to see them. And so if we ever see a Martian or a bug on Mars, you'll be able to see them before NASA has time to censor it, as a lot of the conspiracy theorists say we're doing. And just for those of you who remember when we landed, that image on the top right was our first image on Mars, and you see that it was extremely dirty. When we took the lens cap off, we found that most of that dirt had actually gotten under the lens cap, so we were a little concerned that we would never be able to see things very well with that camera. But here's what the same image just a little bit later. If you can look at the horizon there, you can see most of that dirt has fallen off. We now have our lovely seismometer and our disappointing heat flow in the frame. So we're actually getting excellent images here. We can see clouds moving across the sky with that imager, and we're able to actually measure the dust in the atmosphere. We have lots of other images that are kind of interesting to look at. This is one over there on the far right that I'm particularly proud of. It shows our calibration target, which has the flags of all the countries that have participated in this mission. The InSight mission couldn't have been done without the participation of almost a dozen countries across the Earth. The seismometer was built in Europe. The heat flow probe was built in Europe. The meteorological wind sensor was built in Europe. These are all things that we use the best technology and the best minds from all over the world to do this mission, which I think should be the template for space exploration into the future. And with that, I'd like to thank you for listening, and I'm willing to take questions.
Excellent. Lyra, do you have some questions for Bruce?
Absolutely. Thank you very much, Mr. Banerdt. I have a couple of questions that I'll ask on behalf of the audience. So we got a few questions about dust clearing methods, and I'll read one of them from Roger. Do future lander missions consider including other solar panel dust clearing methods, such as static repulsion, windshield wiper brushes, or even a tiny Zamboni?
Yeah, I mean, these are all things that are considered every time you put together a mission like this. You have to have a lot of trade-offs between cost, complexity, and your objectives. Okay, so the objective of this mission was to last for at least 1 Mars year, 2 Earth years. And by our analysis, we thought that within 2 years we could get enough seismic data to get to be able to satisfy our science objectives, and that turned out to be the case. We were also a cost-constrained mission. We had a certain amount of money to work with. We proposed to do this within a certain budget, which turned out to be about $800 million. And within that budget, we had just enough money to do this. And so to develop a new technology for cleaning off the solar panels, do the testing, prove that it's going to work, prove that after you build it that everything is right. That would have added more cost to our mission, and for us, that would have required us to take off some of the science. And so, for a mission that has a limited lifetime necessity, it turns out it's easier to make a little bit bigger solar panel than it is to develop the technology to clean it off. For a long-lived mission on Mars that wants to use solar energy, I think those kinds of technologies are definitely available. There's a lot of question marks about, you know, how dust adheres to these things, what happens in the Mars environment, and those are difficult technical questions, but they're not certainly beyond our ability to address. And so I think those kinds of techniques will be useful in the future. I would have loved to have the resources to be able to afford those for this mission, but you know, again, you know, you have to balance the money available to you with what you want to accomplish, and this seemed to be the best trade for us.
Thank you. The second question is from Grant, and they're asking, does only having one seismometer on Mars limit what can be learned? What additional learning could be done in the future when we have more seismometers on Mars?
Oh, yeah, one seismometer is definitely very limiting, and we deliberately set our sights at the level that we could do with one seismometer, which is sort of get the global structure of Mars. So in order to really understand the diverse seismic environment on Mars, be able to see the other side of the planet. I mean, the core actually shadows about half the planet from our seismic vision, and so you would like to have seismometers distributed, you know, all around the globe to be able to look at seismic activity everywhere on the planet. And there are many seismic techniques which utilize multiple signals, simultaneous signals from multiple stations. We can just use a very few techniques with a single station. It's enough to get us, again, the basic science that we wanted to get from this mission, but to really understand the interior of the planet, to really understand its current tectonic environment, you would like to have at least a half a dozen stations on Mars. And so I would really love to see sometime in the future a Mars network mission with a half a dozen or more stations, with timing that's coordinated to be able to start to look at Mars in more detail. I think, you know, we've taken the first step, sort of a first reconnaissance. Kind of, this is equivalent to the early mariners, which flew by Mars and gave us our first look at Mars. We now have our first look at the deep interior. Now we need a seismic network, which will correspond to Mariner 9 and Viking, and finally, you know, the rovers, which have given us a detailed look at the surface. These will give us a detailed look at the interior.
Thank you, Lyra, and thank you, Bruce, for participating. Thank you very much, and congratulations on the success of InSight.
Thank you very much.